This is section 3.3, day 3, and we're going to start by a quick review of the product and the quotient rule. So remember, the product rule is derivative of the first expression times the second unchanged plus the first expression unchanged times the derivative of the second. And the quotient rule is we gotta remember our little saying here. We have low d high minus high d low over low squared. So low is the denominator, high is the numerator. So in this case, we're talking about v times the derivative of u. That's low d high minus high d low would be u times derivative of v, and then low squared would be v squared. So those are the quotient and product rules. Let's just take a look at this example here, because we can do this example two different ways. It is a fraction, so we can use the quotient rule. We can also use the power rule with a negative exponent. So let's first use the quotient rule. So here's our quotient rule. So our derivative is then our low times the derivative of our high, which is 0, minus our high times derivative of our low, which is 3x squared, all over low squared. So x cubed squared. And so when we simplify that, this is 0. So we have minus 6x squared on the top, divided by x to the 6th power on the bottom. We can cancel some powers here. We have minus 6 over x to the 4th. So that's doing the quotient rule. Now let's look at the product rule. And in order to do the product rule, we're going to have to write x cubed in the bottom as a negative exponent on the top. And so then our derivative then is doing the power rule on this. So we bring this negative 3 over and multiply it times 2, and then reduce the power by 1, which means it gets one smaller, which is x to the negative 4th. And of course, x to the negative 4th is just x to the positive 4 in the bottom. So you can see we end up with the same derivative either way. So when we have something like this, you really can decide which way you want to go on that, which approach you'd like to use. This is not in the notes, but let's just kind of think about this conceptually. When I say derivative, you should be thinking slope. So when I ask what kind of derivative does a horizontal tangent have, horizontal tangents occur when the slope is 0. So if you think about a horizontal tangent or a horizontal line, it has 0 slope. So the derivative then is equal to 0. So if you look at just this random polynomial function here, where can we find horizontal tangents? And so those horizontal tangents are where we have 0 slope. So we're going to have one up here, and one down here, and another one up here, actually. I almost missed that one, and another one down here. So we have 4 locations with horizontal tangents. It looks like at these locations, negative 2, 1, and 3, and 5. And so if you notice, then horizontal tangents occur at the hills, and like these 2 hills and these 2 valleys. So the horizontal tangents occur at the hills and the valleys, or the peaks and the troughs, or what we'll start calling as the mins and the maxes and the mins. And so we're on this function, a slightly different function. This is x to the 4th minus 2x squared plus 2. Where is the derivative equal to 0 on this function? So we look at the hills and the valleys. So when we say derivative is equal to 0, if I say derivative, you're thinking slope. So where slope is 0 here, and here, and here. So we're going to find then, just find the horizontal tangents of this function. So if visually we can see that, but what if we didn't graph it? What if we just had the polynomial? And we didn't graph it, and we didn't have an easy way of seeing hills and valleys. Well, then our approach that we want to use then is to calculate the derivative. So that's 4x cubed minus 4x plus 0. And we're going to set that equal to 0 and solve it. So we're going to go ahead and set this equal to 0. And when we have this set equal to 0, we always look to factor out instead of just divide out. So I can see that I can factor out a 4x from each term, and it leaves me with the first term of x squared, and then this next term has a factor of 1. And then I can continue to factor this. And so I have x plus 1 and x minus 1. So most of these questions that we ask you will be polynomial, and they should be factorable. So we should be able to factor them into groups, into groupings such as this. And then we can set each one of these equal to 0, because that's a possibility. And when we set this equal to 0, we get an x value of 0. When we set this equal to 0, we get an x value of negative 1. And when we set this equal to 0, we get an x value of 1. So this is where the hills and valleys are on that graph. So taking a look at the graph again, just to go back real quick, 0, negative 1, and 1. So here's 0. Here's negative 1 and 1. They happen to have the same y values. So we can kind of take care of it with a single line. So we have 0 slope when y equals 2 and when y equals 1 at those y values. And so we're going to start graphing now. This is the actual function. It's in blue. We're going to start graphing the derivative now. So for instance, if we take a look at that, that's our derivative. So think about this being a 1, 2, 3, 4th degree polynomial. And when we differentiate this, we lose a power. So we have a 1, 2, 3, 3rd degree polynomial. So in graphing this, we know that we have 0 derivative values here because it's a valley, and here because we have a hill, and here because we have a valley. And this function is sloping downward, which means its derivative is negative. In other words, its tangent lines have negative slope. So it has negative derivative values up to here. So here are all those negative derivative values up to that valley. And then in this area, we have positive slope, and then coming back to 0. So we have positive slope values up to some point here where we have the biggest, steepest line. We call that a point of inflection. We'll talk about that later in the chapter. And then that slope tends to flatten out again and go back to 0. And then likewise over here we have a steep slope, and then it gets to some steepest value, and then it starts to flatten out again. But all these are sloping negative. So we have negative slope values to some sort of steepest point here where we have our steepest slope. And then those slope values come back to 0 at that valley. And then this function turns to be increasing again with in other words, with positive slope. So notice our slope values then go back into the positive region of the graph. So that would be graphing the derivative. And so again, we have 0 slope at 0, negative 1, and 1. So let's extend our thinking here. And we're going to use the derivative rules numerically. In other words, we don't have a graph and we don't even have a function. So we can't use our derivative rules like our power rules and stuff. But we do have function values like function u at when x is 2 equals 3, and u's derivative is negative 4. And function v at the same location is 1, and v's derivative is 2. So we can think of our derivative rules then, like for instance, find the product of u times v. And if we want to find the derivative of that, then we have to use our derivative rules. So it's going to be first times derivative of the second plus the derivative of the first times the second. And all these values are tabular. In other words, they're going to come from this table of values or this list of values. So the value of the derivative is 3. And the value of the slope of v is 2. And then the value of the actual function of v is 1, so there's 1 there. And then the value of the derivative of u is negative 4. So when I multiply these together and then add them up together and then finally add them, I have 6 plus a negative 4, which is 2. So there's the product rule, and this is the derivative of u times v. If we talk about the quotient rule, so we'll call that function z, and its derivative then is using our quotient rule derivative. So remember, it's low d high minus high d low over low squared. And so our derivative then, the value of our low function is 1, and the derivative of our high function is -4, minus our function u, which is 3, and the derivative of our b function, which is 2. So that's low d high minus high d low, and then all over low squared, so 1 squared. So multiplying this out is -4 minus 6, which is -10 over 1. So the derivative of the quotient rule is -10. Another way we can use our derivative rules numerically is to have values of the graph. And so if we look at this, we have function f. So here are function f's values. And then we have, since this is all linear, I know that the derivative values, when I say derivative, we're thinking slope, are the values of the slopes here. So like, for instance, the slope of, in this region for function f, its slope is 1. And here its slope is -1. And here its slope is up 2 over 1, up 2 over 1. So here its slope is 2. And for function g, these are all g's function values. And the g's derivative then are its slope values, and it's also linear. So the slope value in this region is, I'm going to start here, down 1, right 2. So this is -1/2. This slope value is 0. And this slope value is also down 1, right 2. So this is also down -1/2, or its slope is also -1/2. So let's find the derivative of p, and p is going to be the product of f times g. So that being the case, then it's going to be the derivative of f times g plus f times the derivative of g, and that's all evaluated at 2. So it's all evaluated right here. So when x is equal to 2, the derivative of f is 1. So in other words, when x is equal to 2, the slope of function f is 1. So that goes there for f prime. When x is 2, now I'm looking at g. When x is 2, g's value is this y value here, which I'm going to call 3.5. Okay, so 7 over 2. And then I have to add to that f's value. So when x is 2, f's value here is 7 times g's derivative, which is g's slope right here, and g's slope right here is -1/2. So when I multiply this out, I have 7/2 plus a -7/2. So interestingly enough, the value of the derivative of their product happens to be 0. So at x equals 2, the product of these two functions either has a hill or valley, because we have a 0 slope. Okay, using the quotient rule now. So we have our quotient is f over g, so g is low. So we have low times derivative of high minus high times derivative of low, all over low squared. And we're going to evaluate this one at 8, so we're going to be out here. Okay, and so so the value of function g at this location is 2. That's the y value. The slope of f, the derivative of f at this location, is +2. And then we have a minus sign. And then we have to have the value of function f here. Its y value is 6. So we put 6 in there. And then g's derivative, which is g's slope here. So g's slope here is -1/2. So we put -1/2 in the expression. And then we divide that by g squared. So again, the function value of g here is 2. So we're going to divide that by 2 squared. And so when we multiply all this out, it looks like we have 4 minus a -3. So that's 4 plus 3. So that's 7 over 4. So that's the derivative of the quotient of those two functions is 7/4. So that takes care of day 3. So remember our essential question, which we have to go all the way back to day one to kind of review that. What pattern do we see in the limit methods so that we can make shortcuts? And what do we call those shortcuts? So we're seeing patterns in the limit method so that we can do things like the power rule. And that's really focusing on polynomials, which is really kind of all we're looking at this point. So at this point, you're ready to do day 3 of the homework.